Alrighty, hey folks, good to see you guys again here. We're going to keep going through this wonderful world of limits here a little bit. So we talked about evaluating limits, where we just plug the number in there. So say I have a number, and I plug my 3 in here, so I got 3 squared minus 9 all over 3 squared minus 5 times 3 plus 6, I would end up with something called 0 over 0. Well, 0 over 0, this is something that math people call, and again, there's other forms of this, but this is a form of something that we call indeterminate form. In other words, if something ends up 0 over 0, that means originally it was in its indeterminate form. We can't determine what the limit is. So if I were to go and I plug these values in, I plug it 2.8 in for x, I would have got 7.25. So maybe using a table might help me out a little bit here to figure out what this value might be. If I plug 2.9 in there, I get 6.5556, 6.5 repeating. When I plug 2.99 in, I get 6.0505 repeating. 2.99, I get 6.005. And 3, we already saw that was 0. And if you plug that into your calculator, it's going to give you the word error. And then 3.01, we end up with 5.995. 3.01 is 5.9505. And then we have 5.54, repeating. And then we have 5.16 repeating. But if you look at the table, it kind of looks like it goes somewhere. It kind of looks like it goes to that number 6. Even though our calculator doesn't think so, it kind of looks like it goes to the number 6. Well, we have a theorem that says if functions agree at all but one point, then I can rewrite it and use that new form to evaluate it. So we could go through that whole thing, but essentially this is what it says. If I plug a number in, if I plug 3 in here, I get 0 over 0. And we always got to plug the number in first. If that happens, then this theorem we have says, okay, well, let's try to rewrite this in a different way. So instead of x squared minus 9 and x squared minus 5x plus 6, maybe there is an alternate way to do it. And we're going to do something called the dividing out technique. And it's not really, in my mind, it should be called more the factoring technique, because we're just going to factor here. So can I come up with an alternate way that would be the exact same thing as the original function or the original limit, just except at that one point that made it 0 over 0. So if I factor the top and I factor the bottom, I get x minus 3 and x minus 2. And since they both have x minus 3 on the top and the bottom, I can cancel that out. Notice that's x minus 3, that was the factor that was causing my limit to end up being 0 over 0, causing my limit to be in indeterminate form. Because I was saying 0, I wrote 0. Oops. So we have x plus 3 over x minus 2. So if we plug our 3 in here, we end up with 3 plus 3 all over 3 minus 2, which ends up being 6 over 1, or 6. Turned out the limit actually does equal 6. It would just have if I were to graph it, it would have had a hole at that spot. Why don't you guys try this idea of dividing out and see if you guys can actually do the next one. Remember, you first have to plug it in and show me that it's indeterminate, though. All right, so we plug it in here. I end up with 8 minus 10 plus 2 all over negative 6 plus 6. I didn't plug it into the first one up there because we'd already done that at the beginning, and I end up with 0 over 0. So it's indeterminate. So since it's indeterminate, that means I can go ahead and try to rewrite it. So we have 2x, oops, can't do that quite yet. 2x squared plus 5x plus 2 all over 3x plus 6. And if I factor it, notice each time I go over, I'm still bringing that limit with me. All right. Got to make sure we have good form here when it comes to limits. So we always have to rewrite limit as x approaches whatever. So 2x plus 1 and x plus 2. And on the bottom, I end up with 3 times x plus 2. And I looked up above to see the limit I had above. Let's fix that real quick. So the x plus 2's would cancel out. And we have 2x plus 1 all over 3. And if I plug my negative 2 in there, I get negative 3 over 3, which is negative 1. So we originally tried to plug everything in here, friends, and we end up with, oh, what's that going to be? 9 minus 9. And negative 27 plus 27, which is 0 over 0. So why don't you guys go ahead and pause this one and see if you guys can actually rewrite this one to make this one work. Go for it. All righty, let's see here. So the limit as x approaches negative 3. We're going to factor difference of squares on top, so x plus 3 and x minus 3. And on the bottom, x cubed plus 27, that's the sum of cubes, so we'll do that as well. X plus 3, x squared minus 3x plus 9. And actually, I should have wrote the original limit first. Let's just do that real quickly. Because if I'm going to use that theorem, I got to originally show what the original theorem was before I rewrite it. All right, so my x plus 3's, they will cancel out here. And we end up with x approaches negative 3. And on top, we have our x minus 3 all over x squared minus 3x plus 9. So negative 6 all over 9 plus 9 plus 9. So negative 6 over 27, which would be negative 2 over 9. All right, and that's called the dividing out technique or factoring out. Now, factoring isn't the only type of limit, or the only thing we can do to limits to help evaluate them when they're in determinate form. We're going to look at a couple others as well. Now, we're not doing every single one that you could do in calculus, but we're going to cover most of them. But before we go to the next ones here, what I'd like you guys to do is do a real quick thing. I want you to multiply these out real quick. I don't care if you use the box or not. If you want to, you can. If you don't, don't. But go ahead and multiply these out real quick, and let's just remind ourselves what's going to happen. All right, so if I were to take the first one here, x plus 3, x minus 3, I end up with x squared plus 3x minus 3x minus 9. So that this whole idea of the difference of squares, and again, that's using the box. All right, we did that back in integrated 1 and 2. But I'm hoping you guys just remember that when you do this, you end up squaring the first term, you square the second term, and put a minus in between. It cleans itself up. So if I were to do that over here, I square the first term, x squared. Root 5 times root 5 would be 5, so I square the second term, and then I put a minus in between. It's the difference of squares. And the difference of squares, what it does is it gets rid of that middle term, or when we have these radicals, it got rid of the radical from our polynomial. If you remember, when we did imaginary numbers, it got rid of the imaginary as well. So we're going to use that idea here to help us with a couple other ones that use something called rationalizing. So say I plug 2 in here. I get 2 plus 7 minus 3 all over 2 minus 2. And friends, that would be 0 over 0. So that means there's got to be some way that I can rewrite this potentially to evaluate. I may not be able to. Potentially, I need to be able to rewrite it. Now, I'm looking at this and I see a radical in the numerator. Well, that radical caused me some issues. So it'd be great if I could somehow get rid of that radical in the numerator. Now, if I do get rid of the radical in the numerator, please realize it's going to create a radical in the denominator. But like we just saw, if I multiply by its conjugate, and I do essentially the difference of squares thing. So instead of minus 3, I make it a plus 3. That would allow it to clean up so I could actually be able to evaluate it. So we plug it all in there. And then when we multiply it out here, I end up with square the first term, so that's x plus 7. Square the second term, 3 times 3 is 9, and put a minus in between. And when I do that here, I end up with x minus 2 times x plus 7 plus 3. So we have a x minus 2 now in the numerator. And I have x minus 2 in my denominator. So now I'm going to be able to cancel out that factor. So that leaves me with a 1 right there. And then x plus 7 plus 3. Now we can evaluate. And if you notice, friends, I no longer have 0 over 0. I end up able to figure out exactly what that answer would be. It'd be about 1/6. So when you evaluate that limit at x is 2, it would end up being at 1/6. Why don't you guys go ahead and pause the video here and try this next one and see what you guys can do with it. All right, let's see how you guys did. You plug 0 in there, you get 1 minus 1 over 0, which is 0 over 0. So it's indeterminate. So once we know it's indeterminate, we can go ahead and evaluate. So the limit as x approaches 0 of 2x plus 1 minus 1 all over x. And then we're going to multiply by that conjugate again to create that difference of squares idea. So 2x plus 1. And then instead of minus 1, I'm going to have a plus 1 there. All right, so we have the limit as x approaches 0. So we have 2x plus 1 minus 1 all over x times the square root of 2x plus 1 plus 1. So the 1 minus 1, that'd be 2x. Now the x's cancel out. And then when you plug the 0 in there, friends, you get 2 over the square root of 1 plus 1, which is 2 over 2, which is equal to 1. So we can use this rationalizing out idea as well. All right, let's take a look at one other way that we can simplify things, and that's just getting a common denominator. So for instance, say I plug my 1 in here. I get 1/4 minus 1/4 all over 1 minus 1, which is 0 over 0. So we see that it is essentially going to end up being that indeterminate form, which means we might be able to do something else to kind of help ourselves out here. In which case, I can multiply by the common denominator. So if I take my fractions here, and then x minus 1. Notice I don't have a fraction per se in the denominator, so I can just put the whole thing over 1 and make it its own fraction. So I'm going to multiply everything now by the common denominator. So 4 times x plus 3 and 4 times x plus 3 and 4 times x plus 3. And when we do that, friends, the x plus 3's cancel out, and I'd be left with 4 as my first fraction. And the 4's would cancel out on the second one. I'd be left with minus x plus 3 all over x minus 1 times 4 times x plus 3. So now you get rid of our complex fractions. We're down to just one fraction, so we'll go ahead and simplify it now. And we end up with 4 minus x minus 3 and let's see here. I have negative x plus 1. I still have my x minus 1 and times 4x plus 3. So if I factor out the -1 up top, I have -1 times x minus 1. And on the bottom, I still have my x minus 1 times 4 x plus 3. So now our x minus 1s will cancel out. So let's see if we can do that here. And 4 times x plus 3. So now we are no longer going to get 0 over 0. We have our alternative form. And so by plugging it in there, I'll figure out what the limit actually would be equal to. And that equals -1 over 16. All right, friends, why don't you guys go ahead and pause the video here and let's see how you guys do on this next one. All right, let's see how you did here. So we plug that 2 in there, 6 over 2 minus 3 all over 2 minus 2. And friends, that ends up 6 divided by 2 is 3, so we end up with 0 over 0. So it's indeterminate again. So once we see that it's indeterminate, that means we're going to be looking for an alternative form to be able to evaluate this. So these are, that 3 is over a 1. This x minus 2 here, I'm going to put that over a 1. So that common denominator is just going to be x. So I'm going to multiply everything here by x. And when I do that, I end up with 6 minus 3x all over x times x minus 2. So I'm going to factor out my -3. And I have x minus 2 on top. All over x times x minus 2 on the bottom. The x minus 2's would cancel out. I'd be left with -3 over x. So -3 over 2. All right, so now we got using common denominators to help us evaluate. So one other type of little thing we'll talk briefly about, and then we'll go ahead and call it a day here, is something called the difference quotient. Now, the difference quotient is this limit, and we'll talk more about it in a couple days here. It's a type of limit that shows up every once in a while. And we can use it to help us evaluate, or we can use it to evaluate the limit of functions at certain values. So you don't need to show 0 over 0 on this one. It automatically would be 0 over 0 originally. But here's how this works. We know what f of x is. What we really need to know is what is f of x plus h. So when I do this f of x plus h, what I'm really doing is wherever I see that x, I'm going to plug in x plus h into it. So I don't want you to get too terribly lost along the way. When you see that x plus h, that's what I'm going to be eventually doing. So we're going to use this difference quotient to evaluate a special thing with this function. Oopsie. So the limit as h approaches 0, and this is our difference quotient right here, f of x plus h minus f of x all over h. we're going to evaluate it for f of x squared. F of x equals x squared plus 3. So the first thing I got to do is I have to have my f of x plus h. So x plus h squared plus 3. So there's my f of x plus h. And I'm going to subtract my f of x, subtract my original function. And when we do this here, friends, we end up with the limit as h approaches 0. We have x squared plus 2xh plus h squared plus 3 minus x squared minus 3. And if we do this right, anything that doesn't have an h should have canceled out. So the limit as h approaches 0, we have our x squareds cancel out. I have my 2xh still. Then I have it plus h squared. The 3's would have canceled out as well. So this is what we're left with. So we're going to factor out an h out of the top. All right, so 2x plus 0 equals 2x. So right now you might think to yourself, okay, what are we going to do with that? Well, we will eventually do some with that in a couple of days. But for the time being, we just want to get used to this idea of doing a limit with the difference quotient. So why don't you guys go ahead and pause the video and see if you guys can do something with this one right here. All right, go for it. All right, let's see how it works. So we're going to plug it in here. All right. So every place I see an x, I'm going to plug in x plus h. So here we go. F of x plus h. So 3 times x plus h squared minus 5 times x plus h. And then I'm going to subtract the original function from it. So we're going to go ahead and clean that up a little bit here. So x plus h is x squared plus 2x h plus h squared, and then I'm going to factor the 3 in there. So that would become 3x squared plus 6xh plus 3h squared minus 5x minus 5h minus 3x squared plus 5x. And just in case you guys are struggling a little bit to see where that 3x squared came from, I'll go and multiply it out this one time. So x squared plus 2xh plus h squared minus 5 times x plus h minus 3x squared minus 5x. So when we clean up this whole thing here, let's see, the 3x squareds go away. I'm left with 6xh plus 3h squared. 5x goes away, and I'm left with minus 5h. So if we factor the h out of the top, we have 6x plus 3h minus 5. And that would leave me then with 6x plus 3h minus 5. Plug in our 0, we have 6x minus. All right, friends, one last one, and then we'll call it a day. Why don't you guys go and try that and see how you do. Go for it. All right, here we go. The limit as h approaches 0 of f of x plus h minus f of x. So limit we have x plus h cubed, and I told you what that was going to be, plus 2 times x plus h squared minus x cubed plus 2x squared. So I already used the binomial expansion theorem to multiply that one out for you, because I care more about the process than you guys being able to actually multiply that whole thing out there. All right, so let's go ahead and expand this entire thing here. We have x cubed plus 3x squared h plus 3x h squared plus h cubed. And then the 2 times x plus h squared. So that would end up being, when you multiply it out, you get 2x squared plus 4xh plus 2h squared minus x cubed minus 2x squared. And again, if we do this right, anything that doesn't have an h will cancel out. So let's see here. The x cubes cancel out. I'm left with 3x squared h plus 3xh squared plus h cubed. And the 2x squareds will cancel out. I'm left with plus 4xh plus 2h squared. So we're going to factor the h out of the top. So we have 3x squared plus 3xh plus h squared plus 4x plus 2h. And we're going to get rid of that. And the 0 is going to cancel out after that anything that has an h in it still. We end up with 3x squared plus 4x. And that's the difference quotient. All right, friends, we just did a lot with limits there. A lot of just simplifying and a lot of just how do we solve it when it ends up being indeterminate. So we'll talk more about this in class, and have yourselves a wonderful evening.